All right, let's take a look at the next problem here. This problem wants us to determine the time domain capacitor voltage shown below. So remember, for time domain capacitor, or for voltage really, so it's that V of t is equal to V of m cosine omega t plus the phase angle. Well, let's see what we have here. So we have a current source, 1, 2 resistors, and then a capacitor. Okay. So how we're going to do this is we know that this current coming from this source is going to pass through that R1 resistor, and it's not going to change the current, but it'll get down to here, and it'll split some current off this way. It'll split some current off this way. So the capacitor and the resistor receive current. Okay, so let's look at what implications that has. We're going to need to do a current division in order to figure that out. So first things first, if we're working in the complex form, let's go ahead and get complex values for everything. So C of R will be equal to 3.5 ohms, which is just equal to 3.5 at angle 0 ohms. ZC is equal to 1 over J omega C, or negative J over omega C. And our omega is going to come from right there. So our omega is going to equal 500 hertz. All right, but it's actually our frequency. To get it in radians per second, which is what we work with, we needed to do 2 pi f, which will give us 1,000 pi radians a second. Okay, and that's what we need. Okay, so we'll do negative J over 1,000 pi. Our C value is 15 microfarads. And when we do that, let's see what we get. 15 times 10 to the negative 6 times 1,000. Getting negative J 21.22 ohms, which is just the same thing as saying 21.22 at angle negative 90 degrees. All right. So now let's keep trucking here. If we know right here this current is going to split at this node and send some that way and send some that way, to do the current division, what we'll need is, it honestly doesn't matter which one we do, because these two are going to have the same voltage value across them because they're in parallel. But regardless, we need to figure out what the current is going to be through it. So we can do, I'll just go ahead and call this one IFC on the side. So IFC is going to be equal to Z parallel over ZC. And this will be multiplied by the current source, which will be IS, we'll just call it. Okay, but first things first, we had to go find ZP. So to do that, let's do Z parallel, which is this combination here. That is going to be 3.5 at angle 0, multiplied by 21.22 at angle negative 90. we need to add the two. Let me go and write the ZP equation real quick. ZR times ZC over ZR plus ZC. Okay. Just so we're all on the same page. All right, then now I'll just plug in the other values in the bottom. These are going to be the rectangular values. Okay, and notice in the top how we have them in phasor, because if we're multiplying and dividing, we want to use phasor, and if in the bottom, in the denominator, we're using rectangular. If we're adding, subtracting, remember we want to use rectangular. Okay, so when we multiply these out, we get 74.27 at angle -90. Then we need to convert this bottom here, and remember it's just going to be 3.5 squared plus -21.22 squared, square root of that. That'll give us 21.51. Then theta will equal the tangent inverse -21.22 over 3.5. That'll give us -80.63 degrees. Okay, that's just the conversion I'm doing in the bottom, because now what we're about to do is do a division. So it would be helpful to have the phasor available to us. So 21.51 -80.63. When we divide that out, you get 3.45 at an angle of -9.37 degrees. And that'll be in ohms. All right, and we're almost there, so we'll just go ahead and finish this off. So find IFC, the current. We'll plug ZP in, which we found was 3.45 at angle -9.37 degrees over 21.22 angle -90 degrees. All right, and then our source current, we're going to break that off. I guess I can write the IS up here. It's just going to be 10 at angle 0. Just given from that information there, they'll provide it to you in a kind of an odd way like that, where they list it sometimes. Okay, so then 10 at angle 0. So all we're going to do is multiply and divide all these numbers out. So here, let's do this. We'll do 3.45 over 21.22. Then we'll do -9.37 minus -90 degrees. Then we're still going to need to multiply the 10 and the 0, but let's get that in just a second. Okay, and so when we do that, 3.45, okay, we're getting 0.1625 volts, and then our angle is, let's see, getting 80.63. Okay, as an angle. But then we still need to multiply the 10 at angle 0 in. So this would just be 0.1625 times 10. And now instead of subtracting the angles, we'll add them together. So 80.63 plus 0. And this will give us 1.625 at an angle of 80.63 degrees. And that is IFC. So we're almost there. To find VC now, it'll just be IZC. So IC times ZC. So IC, we said, is 1.625 at angle 80.63 degrees. Z of C, we said, was 21.22 at angle negative 90. So just following the same math that we did earlier, 1.625 times 21.22. Our angles here will be 80.63 plus negative 90 degrees. Therefore, V of C will equal I think it is 34.48. Our angle will be negative 9.4 degrees. So if we go and write that out, V is C of t. So in a time function, we get 34.48 cosine. We're going to borrow that omega that we had from earlier. So this will be 1000 pi t, and then minus 9.4 degrees. All right, and that is our calculated answer. Let's see how we stack up. All right, looks like we're pretty close. All right, so yeah, it can get long, but it's very straightforward, just knowing how to manipulate the algebra. So I'll see you in the next video.